yeah, our next speaker is about machine learning systems. Yeah, come up, please. So the next speaker is Professor Henry Xu, Associate Professor from Chinese University of Hong Kong Computer Science Department. His research area is computer networking systems, particularly machine learning systems, and he did a lot of work about smart NIC stuff in data center networks. And Harry has a lot of awards, and like SIGCOMM 2022 Best Paper Award and ICMP 2023 Best Paper Awards. So he will be talking about his, I think, recent work, accepted by SLSP and some related work with it, right? Yes, please.
All right, thank you. So we'll switch gears a little bit here. So I'm going to talk about this very recent work. It's called Minecraft, and it's about tracing the dependencies in all the collective communication operations, for machine learning training. And this is basically a joint work we have with ByteDance and also Professor Ming Lan from Harvard. So, okay, so I'll introduce the background a little bit, but not so much because I guess everyone is sort of already familiar with this entire LM training. So we're looking at the anomalies, and we're particularly looking at these two types of anomalies here. One is called gray failures, and the other is called stragglers. So stragglers is probably very straightforward for you. It just means that you have some ranks, some GPUs that are slowing down the entire process, but the process is still going. So you're still making progress during your training, but you will notice that some ranks are particularly slower compared to the others. Okay, so this is a problem, and it can manifest in both short-term and also long-term kind of time scales. So for long-term, they become the performance bottlenecks, obviously. But a lot of times you also see them like sort of fluctuations, so stragglers as short-term fluctuations. So that's that. Gray failures is a little bit different. So they're probably more severe because they're serious enough to kind of affect the training really, and they will halt the training job actually. But you won't notice immediately when this happens because there's no obvious signal that tells you that something's wrong here and which component is actually wrong here, which rank during this job, or whether it's RDMA, it's the NIC, or it's the network, or it's just the GPU. So during this time when, from when you have the gray failure and, up until the time that you can detect and actually identify the root cause. During this entire time, then your hardware components like GPUs and NICs are basically idle. They're not doing useful work. And also, once you figure out that there is a gray failure, then you have to restart from the checkpoint, the most recent checkpoint, which is wasting a lot of time as well here. Right, so yeah, so I should say that both of them are particularly difficult for industry, like for ByteDance, because they're very hard to detect, because these things spread very quickly. If one rank is having some problem, and then this rank is among like a DP group, and there's some other, it's performing, let's say, some collective communication, and so all the other related ranks will be slowed down very soon. And so what you see from the outside is that they all slow down, but you don't know what exactly is going on, and you can't pinpoint which one is actually having the problem in the first place. Okay, so that's the thing here. Okay, so yeah, so a key problem, a key kind of issue that we have is the lack of observability in this entire process. And I will give you an example of this. So this is a production example. What we have is a defective GPU initially, just one GPU that sort of have some problems. But again, like I said, we don't know that, and we don't see any like exceptions or like nothing throwing up showing up at all. So we don't know about it, but it affects the collective communication, and very soon affects a lot of different ranks. So we see zero network traffic after a little while without any other alerts, just zero traffic. And we actually, in this case, we actually have to wait until 10 minutes timeout from the nickel to notice this. And then we have to, after we see this timeout, we have to go back and try to use different offline testing benchmarks to see which one is actually the defective GPU from all these GPUs. And the final kind of solution that we have to do is to rerun some other model training on multiple machines just to figure out which GPU is actually causing the problem. Okay, so this is really bad. Yeah, so again, the core challenge here is that we don't have the proper or fine-grained observability into what is really going on when some collective communication operations is having problem. And when you see it, it's already quickly spread into a lot of other guys. Yeah, so we think that being able to see like fine-grained system-wide states in CCLs would help us a lot in here, and that's sort of our big motivation of this work. And so this would help us, for example, trace how the anomaly actually propagates, right? Which one is the first, and then how it affects the rest. We can locate the culprit rank, and we can determine the root cause. And we can do this very quickly, and that's the most important thing. So good. We want to have fine-grained observability, but when we look at all these current solutions that we have, there are a lot of limitations. So we kind of categorize them into these three types. Okay. So the first two types, you see a lot of if you work with LLM training, then you probably know a lot of these. So we have, in the first level, we have the so-called OP level or operation level tools. Basically, they work at the granularity of the operation. So what you get is, for example, you get the timestamp of when a overreduce operation starts and when it finishes on each rank. So you get those kind of things. But this, like I just said, this is probably too coarse-grained because you don't really see any fine-grained information as to what is happening when, for example, this overreduce operation is still ongoing, but some of the GPU already got stuck. You can't see that from an OP level tools like this. Okay? And also they don't have this fine-grained information about, for example, RDMA or the NIC. Okay? And also they don't have the anomaly analysis, or they cannot really do this in real time, but they can, some of them can help you to do this anomaly analysis in offline. So that's OP level, and we also have a lot of kernel level tools that can collect a lot of execution traces from the CUDA libraries. So these are actually pretty fine-grained. But the problem with these is that, well, first of all, they are probably too much fine-grained in the sense that once you turn them on, they actually will slow down the operation a lot. So I believe in the later slides we have an example of this. So they would take up actually a lot of bandwidth. They will generate a lot of traces, and use a lot of overhead. And it's probably too fine-grained in the sense that we don't really need that too much information about, when you have kernel launch, what is exactly going on, what's the sequence, execution sequence. Those are probably too much for us. Okay, so that's kernel level tools like Nsight. And finally, we have some couple of tools about RDMA. These are RDMA specific, so they don't really have observability about GPUs. So that's the limitation of the current approaches. So basically, we want to have some new tool, a tracing and also analysis system that can give us fine-grained observability that covers both RDMA, GPU, computer and communication, and that can perform distributed real-time like anomaly analysis without creating too much overhead, like Nsight or kernel level tools. Okay, and another kind kind of key messaging our motivation when we go out and try to do this is that when we look at these collective communications, and we think that the dependencies, there are obviously a lot of dependencies for these CC communication. The dependencies are actually a key in doing this anomaly analysis. And when we are developing our system, we have to capture these important dependencies. Okay? So there are a bunch of them, and we would like to sort of categorize them into these, roughly these three types. So one type is what we call inter-OP dependencies, which is basically, so I'll give you an example here, which basically happens between different, across different OPs. So when you are in training, for example, then first of all, you might want to perform an OR gather so that all the GPUs within the same DP group collect all the updated model weights. And then they can perform training, and then they will perhaps use send and receive to communicate with the peers in the PP group, in the pipeline parallel group, to send their activations or gradients. And so after that, then maybe you go and do reduce scatter to among the DP group again to calculate, to update the gradients. So that's dependency, okay? For example, the reduced scatter cannot start before the send operation finish. It doesn't have the data enough data to carry out the reduce. So the other type, the second type is called intra-OP. So obviously it means there are some dependencies when you look at one single OP. So again, example would be when you try to launch a OP, these are kind of the basic sequence of operations that will have to happen sequentially. So you will have to launch a CUDA kernel and also a NICO proxy process on the CPU side to help manage this communication. And then you can start to copy data to the pre-allocated GPU buffer for your communication, and then you can actually send it out. Okay, and finally, after you send it out, then you will probably try to, because you use IB, so you will have to pull the CQE and just to see if it's finished or not, things like this. Okay, that's just an example. And finally, we have computation and communication dependencies across these two types of OPs. So this, for example, happens a lot when you use pipeline parallelism. You send and receive, like I showed in the above, and then you go ahead and perform your own computation, and then you need to communicate with your PP peer again, so that's another send and receive. These are all dependencies, okay? So we have to collect all of these things when we try to develop a fine-grained tracing system. So that's basically what we did. So we call this co-level tracing, which is co is basically meaning collective communication. Okay, and to be exact, so in order to capture all these three dependencies here, so we're doing these three levels of tracing at the collective communication level. One is what we call trunk level tracing. So we basically try to aggregate the trunk execution data on each component, CPU, GPU, and so on. Chunk refers to basically within the same OP, the transmission actually happens in terms of chunks. You have to divide the data into different chunks. So this is quantified by, for example, the amount of total data transmitted during one OP. So that's trunk level. This would help us collect the intra-OP level dependencies. And also we have the flow level tracing, which is really, really important. And it's really actually missing in the current systems. So what we do is we want to trace all of each and every network flow that is actually associated with a particular OP, for example, or reduce or reduce scatter, okay, including the QPs and the channels that they use. And so we will be able to, we want to basically look at, for example, the spikes or jitter or congestion that kind of happens to individual flows, so that we will be able to tell among all these flows which one is having problem but which one is not. Okay, so that's really crucial, actually. This is really crucial in the sense that initially we want to call this flow level tracing instead of code level tracing. Okay, and finally, we do this in a distributed way because this is kind of obvious because you have collective communication over a distributed system. But more importantly, we want to, so we need to compare, for example, we need to compare all the amount of transmitted data across different ranks in the entire cluster. So that, and according to their dependency information, then we can actually perform anomaly analysis and then try to figure out which one is having the problem and which one is not. Okay, so we trace, for example, the operation types and their sequence numbers locally on each rank. Okay, which one happens first before the other, and then we can sort of maintain the global order and then compare different ranks and see which, for example, which OP have a problem. Yeah, so I'll show you an example of how this fine-grained code-level tracing would be helpful. So if you look at this case here, so the left sort of shows the topology of a few GPUs, and here we actually have a slowdown on GPU 4, which is talking to GPU 2 because they're in the same PP group, and GPU 2 is in the same group with GPU 1 and 3 in the same DP group. Okay, and so basically what happens is that there will be a send operation from GPU 2 to GPU 4 because of PP, and after that, then GPU 2 to 3, they can start the reduce scatter operation because that's the DP process. That's in the DP group. So the first two send operations and the first two reduce scatter operations over here, they're all successful. But starting from here for S3, because like I said, GPU 4 is having some problem, so this one is slowing down first, okay? And so with our fine-grained code-level tracing, you will be able to see these green things and these dark blue bars over here, which is actually the individual network flows that corresponds to these operations. So now you can see them, and then you can compare these two guys, and then you will observe that for these two operations, everything is fine, but starting from here, you know, like this reduced scatter operation is affected because this send operation over here is actually slowing down quite a bit compared to this one. And you know that there is dependency information between these two guys. So when this happens, after a little while, then this operation gets slowed down as a result. Okay? So that becomes very obvious when we have this tracing. Right, so in this second example, we just want to show that if we don't have this code-level tracing, we just use a traditional like OP-level tracing, then it's very ineffective. Okay, so here we're assuming a little bit different case. Let's just say that you have a slowdown in the reduced scatter operation. But what you can see from the OP-level tracing is that you can see a bunch of these timestamps, okay, on different streams. But you cannot really tell that you are having a problem with the reduced scatter operation. And basically, what you can see is the identical timestamps across all the GPUs in the same DP group. Because OP-level tracing only gets the same start and end time stamps. Okay, you don't get to see what's going on actually inside. All right, so basically to quickly summarize, we want to, because of the rapid anomaly spread, so that we want to, when we have anomaly, we want to be able to tell what exactly is causing the problem. And so in order to do that, we need to perform code-level tracing, and we want to do that in a lightweight fashion so that we can do this very quickly without too much overhead. Okay, so that's our main motivation. And so this is the system that we designed, which is called Minecraft. We give it this name mostly because there's a previous system sort of related to this, which is called Sherlock, which is kind of intuitive. So I say, okay, why don't we call this Minecraft, which is the big brother over here. Right, so like I said, it can do anomaly detection, tracing, and also dependency-based analysis to find out the root cause. And we can do it almost in real time, certainly a lot faster than existing tools. So that's the overview of the system, which is not very complicated at all. Okay? So basically what we do is we modify the NICO, mostly the NICO proxy process, so that we will be able to generate and collect some logs. And then there's a separate thread that will continuously collect these information and push it to a remote database. And then we have a sort of another centralized computer that will look at all these data, and then will perform, for example, trigger generation to detect when there is a problem, and we will actually run some analysis, root cause analysis, to find out which one is actually having the problem. So that's basically what we have. Okay, so I'll talk about this in a little bit more detail, but because of the time, so once we post our papers, then you can read our papers for more technical details. So first part is the instrumentation that we did to NICO in order to collect all the traces. Basically, the goal here is to capture data transmission behavior on each device, okay, from NICO proxy. Specifically, we want to collect two types of logs. One is the traditional completion logs, which we only get when a NICO OP is finished. Okay, so these are, the information we collect here include, like, you know, timestamps, start and end timestamps, total amount of data transmitted, and so on and so forth. So that's traditional kind of thing. The other log is really important, which is what we called a state log, or real-time state log. So we generate, periodically generate these logs when a OP remains unfinished. Okay? Currently, we set this period to 100 milliseconds. And we just want to basically use this state logs to see if a OP is actually stuck or it's slowing down. We would still be able to collect some kind of information, and then we can probably see that, you know, this one is slowing down already, and so on and so forth, before we have the completion logs. Okay? Because we only get the completion logs when the OP finishes. Right. Next is trigger generation. So after we have all the logs, they go to the database, and then we will analyze these data as they fly in. The goal here is we want to do this without much overhead, so that we can detect any anomalies almost in real time. So what we do is, first of all, we do sampling, obviously. So here we sample at least one rank from each DP group. Hopefully that covers most of the ranks, because once you have a problem within the DP, it very quickly actually spreads to outside that as well. And the conditions for us to actually trigger, to generate the triggers, here we basically have two conditions. One is that one is for failures and one is for stragglers. Okay? So for failures, we will trigger a failure warning when we observe an OP that is actually stuck in the middle for a long time without any completion logs, but we're getting status logs. Okay? So that one, this would be categorized as a failure, and then we'll throw out a warning. The other type is straggler. So for this, we would generate the trigger when we observe the throughput of this OP that drops dramatically. In the current heuristics, this drops by half, or equivalently when we see that the OP interval increases twice compared to the long-term average. Okay, so that's pretty heuristic, and actually the reviewers actually have some comments and problems about this part as well. To be honest, yeah, I think this is also one of the things that we could look at further. But for now, it kind of works okay, at least in the current production system. And then finally, when we have a trigger, then when we have a problem, then we want to perform analysis to find the root cause, and this is the dependency analysis. So we go here to detect root cause ranks and find the problem. So the basic principle here is that we use the dependency information, and then we'll say that, for example, if we observe a problem during some peer-to-peer communication, then we'll say that if a rank is stuck on a operation with no transmission at all for some extended period of time, then this rank is going to be the problem, the root cause rank. Okay, so that's mostly happens for the pipeline parallel communication. Okay, send and receive. If the OP is the problem OP is ring-based OP, then if it's a ring failure, then we'll say that the rank that has the slowest amount of transmitted data compared to the rest is actually the first one that causes the problem. So because for ring-based communication, everyone is supposed to transmit the same amount of data, but the one that has the slowest amount of transmitted data would be the culprit here. And then for straggler in the ring-based communication, right? So we'll say that the rank that continuously starts or finish the data transmission slower than the other ranks. Okay, so that one is the straggler, obviously. Okay, again, they're supposed to finish around the same time. So, so this is a rough principle, but if you want to go deeper, then we can actually perform root cause analysis to identify, for example, what component, whether it's the RDMA NIC or whether it's the GPU or some other components that actually causes the initial problem. Okay, so we can actually do that with some additional information from our traces. But I guess I will skip this detail for now. Okay, so let me talk about our deployment and evaluation and share some results with you. So we have implemented this as an always-on system, obviously, for training tasks in ByteDance. This is deployed on a server and monitors the training tasks with scales that goes beyond 128 GPUs. And so we're able to monitor and trace up to 20 concurrent training tasks and generating 10 terabytes of data per day. This can also this actually is integrated with a lot of other debugging systems that they already have deployed in their system. So these are just two examples. For example, Flight Recorder is another system provided by PyTorch that gives you traces of the latest operations in the ring buffer. And with these more information, more detailed information, then we can do more analysis to identify the problem. Right? So most of our experiments actually involves injecting faults and failures into the machines and then observe how Mycroft would be able to detect and then pinpoint the root cause. Okay, so this is kind of the setup for our injections. We basically use 32 A100 GPUs in this case. So we have basically four 8 GPU servers over here, and then we have 2 PP groups and 2 DP groups with TP size of 8. Okay, so you can see the dependency. You can see that basically topology over here, and therefore you will see the dependency sort of going on over there. So basically what it says is that if you have a problem, if you inject a problem to GPU 0, then very soon it will affect its peers, for example, GPU 8 in the same DP group, okay, because of the reduce and or gather. And after that, then the problem will propagate to the peer GPUs and the PB groups through send and receive and so on and so forth. That's the deal. Okay, so we have a lot of experiments, but I'll just show you one example here. One kind of type of failure we inject here is a NIC shutdown to see what happens when a NIC is not working. So, so what we did is starting from here, right? Starting from here, then we inject this, we turn down the NIC, and then we see how the traces, we collect all the traces with Mycroft, and then we compare, and then we see how this goes. Okay, so this plot basically shows, the y-axis shows the operation progress that is collected from all the status logs and completion logs. So basically for the abnormal GPU in machine 1, actually very quickly we don't see any logs at all. This is because this NIC shutdown failure is actually injected by us. So it's a software injection so that it not only turns off the NIC, it also turns off the tracing code completely at all. So we actually don't get any status logs. If it's a real NIC failure, then we will still get logs because Mycroft would still be working and give us status logs. Okay, but anyway, so this one you will see it have problem first, and then this peer GPU in the same DP group, which is on machine 2, very quickly will stop generating logs as well. So this one is also having problem. But some other GPUs in the PP group, like this one, okay, this one doesn't really have any injections, so Mycroft is still working over here, so you do see the progress. It's only that they're not really making any progress. It's a flat line, okay? And then the other GPUs in the PP group, they would be able to finish the current reduced scatter, but they can't perform the next operation. They're stuck. But in the same case, okay, in this same case, in here, the NIC shutdown case, if we actually don't use Mycroft, but we use tools like Nsight, then this is what you get, which is basically nothing. Okay? You cannot get even the start timestamps, which is actually already collected, but because the NIC shuts down, and so actually Nsight doesn't really return any traces at all. So this is actually useless if we only use tools like Nsight. So that's a pretty good comparison that I think tells the story a lot. Okay, and even if you do get the traces, basically you can't see much difference across all the GPUs. So you'll see this from here, but I didn't really talk about this injection, this case too much. Okay, right. So this here shows the small overhead of Mycroft. So here we train using Megatron, train GPT model, and then we compare the time with Mycroft to other baseline systems like NVRX and Nsight. And then basically what you see is that Mycroft only adds less than 1% of the total iteration time. So Nsight in this case here with CUDA trace is okay, actually, not too bad. But if you have the CUDA backtrace turned on with Nsight, then the overhead is actually very dramatic. Right, and so this is also the kind of the latency or turnaround performance. So we want to look at so we want to look at the trigger generation time and also the root cause analysis time, and from our production data. And so this here shows the CDF of the trigger time, for example. And so basically, we deployed this starting from November 2024, last year, and we were able to, during the 2 months, November and December, we carried out over 1,200 root cause analysis. And then we see that, you can see from the CDF that 90% of these triggers were detected, generated within 15 seconds of time, and also 6% of them completed the root cause analysis within just 20 seconds, which is very, very fast. Okay, let me use just a little bit time to give you a case study of what we see, what we found with Mycroft. So this is an example with intra-OP straggler propagation. And here we actually, so the figure actually is here, that shows the progress of different channels on different GPUs. So in this case here, we're having a straggler, okay, within a 128 rank DP group. And for each rank, we actually launch 4 nickel channels. And so you can see that, so you can see that the channels 1, 2, 3 of different GPUs, they're making progress, okay. But for channel 0 of the GPU, of this GPU, it's actually having problem. And so that you can see for example, for this red curve, okay, we may not have the legend here, but for this red curve, this is the root cause GPU. So the channel 0 of this cause, channel 0 of this GPU starts to have problem first, and then after a little while, it propagates to the channel 0 of the other GPUs because of the dependency. Okay, and so you can see very clearly how this propagates if we are able to use Mycroft to collect all these chunk level information, right? Okay, so basically the message, kind of the key message that we want to deliver here is, well, first of all, we want to have this real-time capability to be able to collect traces and then analyze what is going on. And so Mycroft is able to do that. And the current tools are too coarse-grained that are not able to actually perform this fine-grained tracing and analysis in real time. And also the other message we want to deliver here is actually the design of Mycroft is general in the sense that although our implementation is based on nickel, but it's very it should apply to all the other CCL libraries. So yeah, and so while we have a very heuristic-based principles, root cause analysis principles, but these also apply to the other CCLs as well. We're trying to work on this. Yeah, we have some ongoing work about better RCA and things like that. But yeah, and also you can use Mycroft with all the other tools, existing debugging tools, to incorporate more traces, for example, flight recorder. Okay, so yeah, so that's basically what I want to say here. Basically, co-level, collective communication level tracing and observability is really the key. And we need to capture all the dependencies among and within the communication OPs as well for our root cause analysis. And the Mycroft is basically designed to exactly do that. And at the end, I want to give a lot of credit to the people that actually did the work, Yang Tao and Lei, who are the co-first authors of this paper. So Yang Tao is the student that did the internship in ByteDance, and Lei is actually the mentor at ByteDance that also worked a lot on this. Okay, and also we want to thank the whole ByteDance's networking team, and also finally Minglan from Harvard. Okay. Okay. Thank you.
Yeah, very impressive work. We have time for one question. Yes.
Hi, Professor Xu. I have one question about, I noticed that your failure detection rule is based on the time gap, like the time gap between two operations, or the slowest rank or slowest server. So based on these rules, how can you ensure that there is no or even zero false positive case, that you detect a failure, but it is not a failure, but just a slow receiver load or slow application? So how to ensure that all the failure you detect is truly failure?
I'm not too sure what false positive means here. So you mean that if you do observe some rank is slower, but it's actually not a problem, or?
Yeah. I mean that in a cluster there is always a slowest rank, but even if it is the slowest one, but it may not be have something wrong happen in that NIC or that server.
I see. So basically, you're asking about one of the principles we have here, whether the slowest one will always be the root cause.
Yeah.
In our from our experience, right, up to now, I don't think there's a lot of problems with that. From the
in the ByteDance, the cluster in your trace, all the failure reported by your system is truly failure.
So at least for the collective communications, so I'm not too sure whether they did this analysis or not, but I think that most of them are actually problems. We actually don't have so many. So yeah, I didn't put the data up, but they don't really have too many these failures and stragglers. Yeah, at least when we look at the data that they gave us within 2 months period, it's actually not that bad. But we didn't specifically look at false positives or other,
Okay, thank you.
Yeah.
All right. Okay, maybe I have a very quick question.
Sure.
So you're most talk about have problems, right? Straggler or some other problem. But did you have any chance that you observed in normal case, everything is normal, for how many collective communications still not be able to hide behind the computation? Any chance to find that number?
They cannot be overlapped by...
Right, computation. In normal case.
Actually, I don't know.
All right.
Actually, I don't
okay.
know.
Yeah. Thank you.
Yeah. So what we did here is kind of heuristic.
Right.
So we would even, for stragglers, we would even say this is a straggler when you are more than 50% slower. Right. But whether or not that is completely right or wrong is yeah. So yeah.
Okay. Okay. Great.
Yeah.
Let's thank the speaker
Thank you.
again. All right, so let's move to the last speaker before our great